All right, boys and girls, it's time for another lesson, and the topic today is Eirgrp. So let me just validate. I am sharing the screen with you guys today. Yes, eventually it looks like I am sharing the right one. Let's move forward. So, um, as always, good morning, good evening, good afternoon. Let's go ahead with the lesson. Enhanced Interior Gateway Routing Protocol, Eirgrp. So, let me go ahead and stop the video for a moment and let's go ahead and focus on the concepts for this one. What is the agenda for today? What are we going to cover in this one? Okay, we're going to cover an introduction to Eirgrp, why choose Eirgrp advantages, key concepts, protocol basics, the magic of dual, Eirgrp metrics and composite metric, um, the basic configuration of a lab, the validation of commands, and a summary of the topics. So let's start with this one. What is Eirgrp? Well, what comes to mind when you think about Eirgrp? Eirgrp is an enhanced interior gateway routing protocol. A Cisco mm, proprietary advanced distance vector routing protocol, also called a hybrid protocol, designed for scalability and fast convergence in enterprise networks. It uses port number 88. Okay, the protocol port number for EIGRP is 88. Some of the benefits of using EIGRP. We have fast convergence. It uses dual algorithm to find loop-free backup paths instantly. Low network overhead, only sends incremental updates when a change occurs. BLSM and CIDR support, fully classless protocol, scalable, efficient for both small and large network enterprise networks, multiple network layer support, originally supported IPv4, IPv6, IPX, and AppleTalk via protocol-dependent modules, PDMs. Next, how does EIGRP operate? It uses three tables. We have the neighbor table, topology table, and routing table. The neighbor table lists all the directly connected EIGRP routes. It lists of directly connected EIGRP routers built using hello packets. So we have the EIGRP routes and routers in the neighbor table. What about the topology table? What is the function for that one? It contains all routes advertised by neighbors. This is the map of the network. And we finally have routing table. It contains the best successor routes from the topology table. Let's move on. We're going to learn a little bit about the brain of EIGRP and dual. Dual, what does dual mean? What is it? Let's go with that one. The brain of EIGRP is called dual, diffusing update algorithm. It ensures loop-free paths at every instance. It selects the best path, the successor, and a backup path, the feasible successor. It can certainly conditions where it's actually meet. This is why EIGRP converges so quickly. It often has a backup path pre-calculated. How does EIGRP chooses the best path? Well, EIGRP uses a composite metric based on bandwidth and delay mainly, but there is also some additional values like load and reliability. By default, only delay and bandwidth are used to calculate the metric. So the formula is basically that we have the metric of 256 multiplied by 10 to the power of 7 is basically the slowest bandwidth plus um, the sum of delays. That's basically what we have. So the formula is 2 multiplied by 2 to the 10 to the power of 7 divided by the slowest bandwidth and then plus the sum of delays. That's the formula that we use to calculate the metric for Eirgrp. Moving on, this is a lab that we will go into detail later and we will configure basically. So you have an understanding and an idea how can we configure an Eirgrp lab successfully. We will look into that in a moment. For now, let's just take a look at an example of a basic Eirgrp configuration. And give me just a moment so I can explain. First, we go ahead and we access the device with the enable. We go to the configure terminal and we add the Eirgrp process here. Router Eirgrp 100 in this example, then the network 10.1.1.0. There is the wildcard mask. It's not mandatory per se, but in this scenario we have it there. Network 192.168, 1.0. Let's just say the wildcard mask will be 0000.255, for example, 255. And that is another example, but remember the mask or net mask is not mandatory. And then we do the no auto summary in order to have a successfully configuration for Eirgrp. Let's go ahead and clear these notes and move on with the presentation. This is the same example. Now we are working along with router 2. Let's say we have the same net mask in here, but remember this is actually 255, the wildcard mask. So we forgot that in the previous one. We have to use this one, the wildcard mask as well. So this is another example, but basically we are configuring this in router 2 and router 1 with the same exact configuration. Last time we may have not uh, got the correct wildcard mask. So please be aware that we will be using similar to OSPF, a wildcard mask. Let's go ahead and clear the drawings and let's move forward. The next thing is commands. So let me go ahead and highlight for you so you can have an understanding about which can be a couple of important commands. We can be working with the show IP Eirgrp neighbors, show IP routes, show IP route Eirgrp, show IP Eirgrp topology. So in the first one, show IP Eirgrp neighbors, this checks if routers form an adjacency. The second one, show routers learn via Eirgrp marked with a D as in Delta or a David. This is show IP route. It shows the route learned via Eirgrp, and usually there is a D. There is a D for those specific routes. Show IP route Eirgrp shows only Eirgrp routes, and show IP Eirgrp topology shows the full topology table. That's basically what we have. Let's go ahead and move on with the next slide. And here we have an output of the show IP Eirgrp neighbors. If you can take a look at this one, let me just change the color here for a moment. And this is what we have. Show IP Eirgrp neighbors, and we have the IP address, the interface, the uptime, and some additional information like the milliseconds SRTT that we will learn about that in a few minutes. Basically, the most important is the address, the interface, the uptime, and the hold down timer, in this case, is 12 seconds. Those are the most important ones. So let's just focus on those for the meantime. You can also see the autonomous system for Eirgrp right there in the second one, and the first one, it is always there. And you can see actually that we are working with router one only, looking at the neighbor, which is in this example, 192.168.12.2. Let's go ahead and continue moving on. Um, for details, it's not that much important to learn about the SRTT, but at the end of the chapter, maybe we can go and do some research about SRTT in EIRP and what do you need it. So let's just leave it for the end of the chapter. Next one we have that the important is the neighbor's IP address, the local interface connected to the neighbor, the whole timer countdown, and how long does the neighbor relationship has been. And finally, we have the last one. Let me just clear the board for a moment. And this is what we have there. EIGRP is a powerful, scalable Cisco proprietary protocol. It uses three tables, neighbor topology and routing. Dual algorithm provides fast loop-free convergence, composite metric. We have bandwidth and delay. It determines the best path. The configuration is simple. EIGRP, then the autonomous system. It was not like a process. It is called autonomous system. Please kindly be aware about that. And then we have the network statements for the different networks that we are using. Remember, the mask is not mandatory. Um, we can either use it or not. But it was not a mask per se. It was while um a wild card mask is a wild card mask. So you are aware of that. Remember that. Always verify with the show IP IGRP neighbors and show IP route. So those are basically the guides that we have for today's lesson. Before we close and we wrap up this lesson, let's just do some research with our little friend ChatGTP. Let's go ahead and do that. We are trying to discover why is it important to have this in this metric that we were working on before, uh, SRTT. So let's go ahead and do some research here. Let me see if we can go over that. So it is SRRT importance in EIGRP. Let's go ahead and find out what is SRRT is the average runtime time in milliseconds. It takes for a packet, usually EIGRP reliable transport protocol packet like updates, queries, or replies to go from one router to a neighbor and back. It is a smooth value, meaning it's average over time, not just a single measurement, to avoid wild fluctuations. So that is basically the meaning about SRTT that we want to know. For the time being, let me see if we can learn a little bit more about the RGRP to close and wrap up for the lesson. So we studied a little bit about the neighbor table. It lists the directly connected neighbors, the next hop routers, the interface, the EIGRP topology table. It basically tells us about all learn routes from all EIGRP neighbors. We have the destination, we have the metric, and finally the global routing table. Best routes from EIGRP topology table will be copied to the topology table. So let's go ahead and clear the drawings for a moment and let's continue moving on. Let me share the video with you guys. Okay, what else do we have? EIGRP will start sending hello packets to our routers, just like OSPF does. If you send hello packets and you receive them, basically they will become neighbors. EIGRP neighbors will exchange routing information, which will be saved in the topology table. The best path from the topology table will be copied in the routing table. Then we have this example of the advertised distance. In this case, we have a total of 5 over here and a total of 10 over there. This advertised distance is in fact 5 for now, only 5. There is a distance of 5, 10, and 5. So let's continue moving on. And now we have that this topology has an advertised distance of 5 only. Okay, let's go ahead and clear the drawings for a moment and try to understand this better because it might be a little bit confusing at the beginning. So we already went over bandwidth, delay, load, and reliability. Those are some of the metrics for Eirgrp. What else do we have here, which is important? The distance for this one is 5. So let's validate why real quick. Let me just clear the drawings. So router card, in this case, router card is this one, will advertise to router N, which is this one. It metrics toward the destination. Basically, router card, it says to router N, it cost me 5 to get here. So the advertised distance is 5 because it's the first thing that we got in order to get to that specific destination. This is the advertised distance, what it costs to get from one location to the other. Okay, let me see if we can have a better explanation about this. Let me continue learning and showing you guys about the advertised distance and how it works. So after the advertised distance, we have the visible distance. Let's learn about that one. We're not done yet since there is something else. Router N will save in its topology table. We now know the distance that it has is actually a visible distance of 15. Let's find out why. Well, in order to get from Carl to Anne, it spends 5. 5 as the advertised distance. But now, why do we have a total of 15 here for the visible distance? That's the great question. Okay, because it is counting this part and this part from on to get to the destination, for example. Now, if we continue moving forward, there is another advertised distance of 15. Now that we have 10 plus 5, we got 15 to get from Ant to King Kong. All right, so the visible distance, in this case, it was 15 and 5. This topology and the other topology for King Kong, we have an advertised distance of 15. Let me go ahead and clear the drawings for a moment here. Okay, we are not done yet since router King Kong also is running Eirgrp router and is sending its visible distance towards router King Kong, which is 15 in this case. Router King Kong will save this and the information now might change a little bit in the next couple of seconds because we have the following. We have 5 plus 10 plus 5, a total of 20 for the visible distance that will come and appears to be at King Kong. So we have an advertised distance of 15 because we are counting these two hubs, number 1 and this other to the destination. But now we have a visible distance of 20 because we are counting everything here. 5 plus 10 plus 5 is actually 20. The first one was only what it cost us to get to car. That it was only 5. And to get to ant, we are counting. This 5 plus 10 is 15, the visible distance. Now, we already have 15, and that's what it costs us to get to and moving to King Kong location. So we already have that 15. Now we want to know the feasible distance is 5 plus 10 plus 5. That is the feasible distance to get all the way from the destination to King Kong path. So that's making a little bit of more sense now. We're fully understanding better. This is a little bit of a practice and calculation. So keep that in mind. Let me clear the drawing and move on. The best path for the destination is called the successor. The router will be copied from the topology table to the routing table. With the Eirgrp, however, it's possible to have a backup path which we call the feasible successor. How do we find out if we have a feasible successor? Let's find out. In this case, we have 5 and a 10. This one has a 5 and a 5 and 110. Let's try to understand this topology. We have some routers. We have King Kong, we have the destination, we have Carl and Ann once again. So in the example above, we need to calculate and find out the feasible distance. Now, the advertised distance, we have 10, 5, and 9 for um, King Kong, Carl, and Ann. So let me just highlight those. We have actually 10, 5, and 9, and that is the advertised distance for King Kong and Carl. That's the advertised distance. Now, let's continue moving forward and see what is the feasible distance. In this case, let's clear the drawings, and those are 15, 10, and 109. Where do you see those? Where do we see them? It's actually 10, 15, 10, and 109. Let me see the calculation. Let me go back to the calculation. Let's go, let's go. Let's go to that topology. So the feasible distance here will be a total of 109, meaning we have, let me just go to the pencil. We have 100 plus 9 is 109. That's the FD, feasible distance for this path. Then 5 plus 5, that is 10. 10 is the other FD for this other path. And then we have 5 plus 10 is 15. 15 will be the other feasible distance for this last path. So we have the path for King Kong, we have the path for Ann, and the path for Car. Those are the paths. And that's basically what we're doing. We're just doing this sum for this route. That's what we're doing. Let's clear the drawings and let's continue moving on to see if there's something else. Finally, we got this successor, which actually um, the lowest administrative distance and the lowest feasible distance in this case will be Ann. So the answer to the second question is, do we have a feasible successor backup path? We need to analyze the formula. Advertised distance is lower than the feasible distance. And in this case, we have a feasible successor here. Um, Now, let's validate something. This is the successor because the feasible distance is lower, is higher than the advertised distance. But this other one is talking about the feasible successor. In this case, the advertised distance must be lower than the feasible distance. And it looks like it is this other one. This other one. This one is the feasible successor. We already have the successor with the lowest administrative distance and feasible distance. Then after that, we have the other one where the advertised distance, this is the AD, advertised distance, is lower than the feasible distance. Meaning this one right here will be the feasible successor, and the other one was the successor. Now it's getting more clear. We are finally understanding this. Let's continue moving forward. Let's see what else do we have in these explanations. And there is another example where you have 7, 9, 3, 4, and 5. This is the following. We have diamond, clubs, spade, and hearts. Um, this is actually the advertised distance is 5, 25, and 19 for those. We have 5 for spade. This is actually right here. Then what else do we have? We have 25 for clubs. Where is that 25 comes for clubs? That's the big question. We have 10 and then 19 and then what else? What else? This actually is only summarizing and adding. There is 9 plus 9 is 18. 18 plus 10? 18, 18 plus 10 is only 28. See if we count everything, but we're not counting everything. Let's see how is that calculation being done. Let me just clear the drawings for a moment. Okay, so how are we getting this one? I got the 19 for diamond. That was actually, let me see the route. Uh, it was 4 plus 5 plus 3 plus 7 is actually to get to diamond a total of 19. Now, how do we get the 25 is the big question. How do we get the 25? Because this is route to get from here to diamond. So maybe we're missing something. What was the last one? What was the one for 25? It was clubs. Clubs is 25. Hmm. Let me see. Let's check. Let me just go ahead and pause the recording so I can try to understand this better. 25. 25. Why is it 25? 25. 5 towards the heart. It's 19 plus 18. Marcos will advertise 5 plus 4 plus 9 plus 7. 25. 5. 5 plus 4. 5 plus 4 plus 9 plus 7. Okay, this is the other route to get to clubs. Okay. So actually the 25 is this other route getting from the specific destination to clubs, and it's actually 25. It's uh, 5 plus 4 plus 9 plus 7. Let me see if we can do the math better. So 9 plus 9 is 18. 18 plus 7 will give us the final answer. So we have 18 here, we have 7. We are doing 7 plus 7 is actually 14, plus 1 is 5, is 5. And this one, there is a 1 here that goes here, and we added 1 plus 1 is actually 2. We got 25. This is a sum. And that's the way that we are able to get the other one from here. So let me just clear this, and let's move down. And you will see the explanation. So the diamond, router diamond will advertise 5 plus 4 plus 9 towards router clubs, and we get a total of 18. Then the other one was 25, which it was 5 plus 4 plus 9 plus 7 is the last one that we were doing. Split horizon doesn't apply here since router clubs learn about the destination in another interface, router diamond. So let's clear the board. Are we missing something important here? We have pretty much practiced everything. Okay, if we continue counting the whole distances, and we already did the calculation when we were calculating almost everything. We got the 28, we got the 28, and the 9 for the feasible distance. Let's see that 9 for the spades, to get to spades. How do we get it? To get to spades. Let's see. So we got a total of 5 here and 4. We got the ninth to get to space. That's it. 4 and 5. Now if we count the rest to get to um either it was the whole route to get to either clubs or to get to diamond. Those were actually 28. Let's validate that. Let me go ahead and click the drawings and validate that. Was it diamond and clubs? Yes. Yes, it's actually clubs and diamonds, and we got 28 there and 28 and so forth. In this one, the successor is mm, um, the one with the lowest visible distance and administrative distance, which is spade. Now, remember the rule, the advertised distance must be lower than the visible distance for the backup successor. So the visible successor, what will it be? So remember, the advertised distance has to be lower. In this case, they both qualify. Interesting. Let's see how we determine this one. Let me clear the drawings for a moment and see the explanation here. So the advertised distance is 25 and 19. Those are the advertised distance. Let's clear this other one. Let me go to the eraser for a moment. Okay, now let's understand this better. We have 9 for spades, 25 and 19, but we already know this is the successor. So the advertised distance of router clubs is 25 and the diamond distance is 19 are higher than the feasible distance of router spade, which is 9. So they won't be a feasible successor. Okay, interesting. So since those advertised distance are higher than the feasible distance, in this case, this one, which is 9, we will not have a feasible successor in this example or scenario. If your neighbor is closer to the destination than your total path, you at least know it's not getting to the destination by sending packets through your router. Perhaps it is not the best path, but it's absolute 100% loop free. Okay, and these are the metrics that we commented before, and we were talking about those. Um, do you guys remember the metrics? We have bandwidth, delay, load, and reliability. Those are the specific metrics for Eirgrp. What else are we missing? Okay, this is more calculations. We already went over that one. Carl, Anne, and King Kong, and we already studied about those. Let me clear this drawing for a moment. Let me just look for that eraser if I ever get to it. Okay, and let's see. Okay, they're talking now about the variance command. The variance command works as a multiplier. Basically, it multiplies. So in order to load balance, our feasible successor needs to have a lower feasible distance than the successor. Okay, interesting. I think the variance command goes. Mm, Now that I'm going to set the variance to 11, this is going to give us the following. 10 plus 11 is 110. Let's see the whole summary of this one and the calculation. So the feasible distance of the successor is 10 plus 2, so we get a multiplier, we get 20. 109 is higher than 20, so we do not do anything, any load balancing. If the variance is 5, we get 10 plus 5, we get 50. So 109 is still higher than 50. So still no load balancing. Now, if we set the variance to 11, now this is what we get. The feasible distance is 10 by 11 is 110. 109 is lower than 110. So now we will put the feasible successor in the routing table and start the load balancing. Are we ever going to use the route through the router King Kong? No, we won't, since it's not a feasible successor. We're almost done with the Eirgrp, but there's one last thing that we want to talk about, and those are let me just clear the drawings for a moment. The keys. Let's talk about the key change. So the key change can be different per router. When we're talking about routers, it can be different. The key change can be different per router. The key ID has to be the same for every router. So that's basically when we're talking about authentication running along with Eirgrp. The key change can be different per router, but the key ID must be the same one on everyone. So just for you to be aware about that. Finally, the key string per key ID, which is the password, this of course has to be the same. Okay, this is the node to summary. This is the network command, router EIGRP. I'm trying to see if we have an example of the authentication. Show IP IGRP neighbors. We already went over that. The configuration of EIGRP. Show IP IGRP neighbors. Pretty much the same information. Address interface, hold uptime, and SRTT. Show IP route. Okay, I'm not seeing like an example of this is the variance command set as free. I'm looking for the authentication example to see if there is okay, there is. So we are configuring a key change. In this example, this is what we have. We have key change, my change, key one, key string, banana. That's the first example. Then we have the other one, both for King Kong and Nan, and it's basically the same. My change, key one, key dash string, then banana. That's pretty much the same. Then we do the following. We add to the interface IP authentication mode EIGRP1 MD5, IP authentication key change EIGRP1, my key change. Those configurations will be added for both router King Kong and router N. In that specific interface, FA0/0 for this example. What else are we missing, guys? Boys and girls? What do you think? Are we still missing something? Let me just clear the drawings and continue moving forward. I think that's pretty much it. If the IP authentication mode EIGRP command is used to enable MD5 authentication and IP authentication key change EIGRP, do select the correct key change. And there is some GNS3 Vault labs for beginners with GNS3, but we're not going to cover that yet. Maybe later on we can do some GNS3 labs. For now, that's everything we need to cover. We have covered pretty much all the basics and fundamentals for EIGRP. So I hope that you have learned about this lesson. You have learned about EIGRP and how to use it correctly in your day-to-day daily work, uh, in your functions as a network engineer and administrator. So, boys and girls, it's been a pleasure working with you today. Take care until next time, and I'll see you at the top of success. Goodbye.